Thank you very much, Joan, and thank you very much to the organizer for giving me the opportunity to present this work, which I've been doing in collaboration with Federico Galli, Rob Myers, and Ignacio Reyes. So let me start, first of all, by telling you what our proposal is for these rainy second laws and reviewing some background material. Okay, so let's say the broad motivation from this work comes from the interest in recent years on the study of very complicated gravitational processes, such as black hole mergers. And these type of processes require very advanced numerical relativity simulations, which are computationally demanding. And so one question that one naturally can ask, and that, let's say, broadly motivates our work, is trying to understand what we can learn about the evolution of black holes without having to solve Einstein's equation explicitly. And so the most famous result in this direction is surely the area theorem by Hawking, which proves that the event horizon of a black hole is a non-decreasing function of time. Yeah. And so this is a geometric constraint that it's able to put restrictions on gravitational dynamics without actually the need of having to solve for the dynamic itself. And so the textbook example that we are all familiar with is the coalescence of two Schwarzschild black holes, let's say of identical mass, small m, which merge into a final state black hole of mass capital M. And so if we are in 4 flat space-time dimensions, the area of the event horizon scales like the square of the mass of these black holes. And then from the area theorem, we can obtain immediately a lower bound on the mass of the final black hole that forms. And this is usually given actually in terms of an upper bound on the amount of gravitational radiation which is emitted in the process. And this is quantified by the efficiency, epsilon, with which these dynamical processes convert the initial rest mass, which is 2m, in gravitational radiation. And so one, it's clearly the theoretical upper bound on efficiency, which is not achieved by any process in nature. And the upper bound on efficiency of this process is given by this number. But then, through the laws of black hole thermodynamics, which associate a notion of entropy to the area of the event horizon, we know that the area theorem is a geometric realization in this context of the second law of thermodynamics, so that the entropy of an isolated system can never decrease. And so as such, for this type of processes, the second law, or equivalently the area theorem, puts a necessary condition, so one single necessary condition for any transition between states described by density matrices ρ and ρ prime. So if we take a look at the, let's say, space of states that we can have, and these represent level curves for the entropy. So what we have is that the second law essentially selects regions in the space, or better, excludes regions in the space of states which are not viable endpoint states for our dynamics. And so one natural question, and that's the question that we have been asking, is whether this second law is one single monotone for the dynamics of the system, or rather just one member within a broader class of monotones. So whether there exist additional laws that further constrains with necessary condition the transitions between states, and thus further restrict the space of viable endpoint states. So this question, at least to my knowledge, was first asked within this context, so in the context of quantum thermodynamics. And so these two works and many others, which I apologize, the citations are not complete, were able to show that indeed there do exist new additional constraints which can be formulated, and they were found to be in general non-trivial for equilibration processes, both of quantum systems, but also of macroscopic systems which have long-range correlations. And I will give examples of such quantities in a moment. So for the moment, let's just call them one such quantity D. And so these are quantities that are able to provide a notion of distinguishability between states, and which are monotonic under transition. And so, for instance, this such quantity D provides one further necessary condition for a transition between rho to rho prime. And so if now we take into account this condition and superpose the level curves for this quantity, this further restricts the region of allowed endpoint states. And so our proposal is to try to explore this type of constraints a bit outside of the field where they were originally formulated, which is essentially the quantum information, and try to, in this talk, see what do they imply for gravitational dynamics, and in particular for black hole mergers. Okay. So the most famous example of one such quantity is the relative entropy, which we know it's a useful measure of the distinguishability of two probability distributions, here rho and sigma, which are usually referred to as the target and reference state. And that was proven long ago to be a monotonic quantity under completely positive trace preserving maps. And just to, let's say, give an example, so this class of evolution includes both unitary evolution and partial trace. So the relative entropy is monotonically decreasing under this type of evolution, and it's also connected to the usual standard Neumann entropy. So to see that, it's enough to consider the reference state to be the maximally mixed state with uniform distribution. And so then the relative entropy with this reference state reduces to the Neumann entropy up to a factor, a constant factor, which measure the, let's say, effective dimensionality of the Hilbert space. And so if moreover the maximally mixed state is stationary, so this is preserved under CPTP evolution, then also the Neumann entropy is monotonic. So let me remind you, just repeat it. So this is true only under these two assumptions. So that we are looking at CPTP evolution, and the maximally mixed state for our system is a fixed point of the dynamics. And so under these assumptions, then we can recover the second law of thermodynamics for our full system as a statement of the monotonicity of relative entropy. Okay, so now these two quantities, von Neumann and relative entropy, have Rényi extensions that we are all very familiar with. So for instance, Rényi entropies and this form of Rényi divergence that I will consider. They're defined for, well, integer m, bigger or equal to 2, and then their analytical continuation, if available, gives us for n going to 1 the von Neumann and relative entropy. And the other two interesting limits here for our discussion today will be the n to 0 limit of the Rényi entropy, which it's known as the Hartley entropy, as is a measure of the number of non-zero elements of the density matrix, and the mean entropy, which is instead the n to infinity limit, and which captures the maximal eigenvalue of the density matrix. So this type of, these Rényi extensions also satisfy similar properties to their n to 1 parents, and in particular, this form of Rényi divergence that I've shown before was proven in more recent years to be also monotonic under CPTP evolution. And so these type of quantities also provide additional constraints along the evolution, and this is like a very non-complete list of works in which this type of constraints have been studied. But now we want to go one step further, and so they make the same argument that we had before. So now if we consider the maximally mixed state as reference state, again, the Renyi divergence reduces to the Renyi entropy up to an additive factor. And so if now the maximally mixed state is stationary, then the monotonicity of Renyi divergence implies the monotonicity of Renyi entropies.
For all n, is that for all n in the complex plane, or all positive real n, or all n greater than 1, or which all n?
Right. So okay. So so these quantities are defined for integer n greater or equal to 2, but then one can find the analytic continuation, and these were proven to be monotonic from 0 to infinity if the analytic continuation is available. Then there are other forms of Renyi divergences for which the proof is not complete, so they only restrict to certain, there are like the sandwiched Renyi divergences, but okay, for this form, yes. Sorry?
When d goes to infinity, all these inequalities also hold?
Right, so here we are a bit extrapolating to quantum field theory, you're right, so yeah, sorry. So indeed, here there is this D, the dimensionality of the Hilbert space, as the way that we are thinking is that somehow we are fixing if we fix the energy of our system, even if D is strictly speaking infinite, the states that we can access in our system are a finite number, and so there is an effective dimensionality of the Hilbert space, which is in fact finite. Okay, so the states that can be accessed at a given energy or with some given initial conditions. Okay, so then also Renyi entropies under these two conditions, so CPTP evolution and a maximally mixed state, which is a fixed point, are also monotonic for each n. And so they provide a one-parameter family of necessary conditions for transitions, which extend the ordinary second law, and that which we will refer to here as Renyi second laws. So just to distinguish them for the ordinary second law. So this type of constraints are well studied in information theory and also in condensed matter systems. So our proposal here is to try to extend these constraints to black hole physics and try to see what do they imply.
Something interesting, or is known?
Whether they do say something interesting, like in condensed matter systems. Well, we will be doing essentially kind of ordinary thermodynamics, because I will use the thermodynamical description of black holes to evaluate these objects, so we will see more detail in a moment. In general, to my knowledge, for the, let's say, this or simple systems where they've been studied, they are not the most stringent constraints, so they are not the most interesting to look at. So they're actually part of a much broader class of constraints, which are known as H divergences, which encompass all these constraints and many more. They're like constructed from two probability distributions, and they have to satisfy some convexity properties. And this is just like one very, just one corner of this huge class of constraints. And what people normally do is to try to scan the space of these H divergences and try to identify the most stringent constraints within this class, and then try to evaluate those. And actually there are also attempts, that was in my outlook, but to trying to trade solving equation of motion for the if and only if constraints, which is much easier to do in some simple systems. Yeah. Okay. So let's try to apply these constraints to black holes. And see what do they imply. But before we do that, there are some important points that I want to make, which are generic and very important. So the first one is about ensemble inequivalence. So we are much more familiar with the concept of ensemble equivalence, meaning that even though the microstate description in different ensembles take a very different form, in the strict thermodynamic limit, they all give rise to the same entropy function. So what I mean, for instance, this. So if we compute the canonical entropy or the grand canonical entropy, these depend on chemical potential, mean values, and the partition function. And these two quantities are in general different, but in the strict thermodynamic limit, there exist relations between the two. And so the canonical, for instance, and grand canonical entropy coincides, and they give a unique notion of entropy. And so this is the important consequence that the physical constraints that come from the second law of thermodynamics are ensemble independent. On the other end, Renyi quantities, such as Renyi entropy and Renyi divergence, they do not only capture mean values, but they capture fluctuations. So they are sensitive to the response of a system under perturbation, and so are by definition ensemble dependent. So this is just one example to make manifest this difference. So this is the canonical Renyi entropy and the grand canonical Renyi entropy expanded to first order around n equal 1. And so we see immediately that the first order correction are different. And this is true for, I mean, they depend on variances, so they differ. And that's true for all higher corrections. And so the important, very important point is that all constraints that come from these Renyi extensions of the second law are ensemble dependent. And this is not something that we are usually familiar with. A second general remark is the following. So in general, these constraints will be non-trivial, so they won't be redundant to the second law, but we can ask a priori whether there are instances in which they are redundant. So this will surely be the case if the Renyi entropy factorize in this form. So if we can write the Renyi entropy as some n-dependent functions times the entropy of the system, then this will drop out from the inequality and the constraints will be redundant. So this is what happens in the microcanonical ensemble if we fix the energy of the system within some small band with delta E. We can write the normalized density matrix in this form, and then it's immediate to compute the microcanonical Renyi entropy and see that they coincide with the entropy. So in the microcanonical ensemble, we do not expect any new constraints, so we have to look somewhere else. That's true also whenever the entropy is an homogeneous function of the charges. So by this I mean that if we rescale, for instance, the entropy depending on these two charges, m and q, and then if we rescale them, and it can be written in this way for some exponent nu, then by thermodynamical arguments, one can show that the Renyi entropy factorize in this form. So whenever this happens, again, the constraints are redundant. And I will tell you in a moment. Okay, but so in general, they are not going to be redundant to the second law. And so our proposal is to try to apply them to the study of black holes, and in particular here I will talk about black hole mergers, and try to put bounds on those processes, just like as the first slide with the original Hawking example that we saw. So of course the most tempting things will be to apply them directly to Schwarzschild black holes, so black holes in flat space. And for those, it's immediate, given the arguments above, to see that in the canonical ensemble, which is the one that where we expect something non-trivial, the Renyi entropies in d space-time dimension can be rewritten in this form. And also it's immediate to see that do fail to satisfy, importantly, 3 of the fundamental inequalities of Renyi entropies. And this should not be a surprise. That's because the thermal ensemble in flat space is not well defined. Schwarzschild black holes have negative specific heat. Their temperature increases as they get smaller and eventually evaporate, and clearly the maximally mixed state is not a fixed point. So unfortunately, in this form, we cannot apply these Renyi laws to Schwarzschild black holes. I will tell you towards the end instead of another set of constraints that we can study for flat space black holes. I cannot hear you, sorry.
How are you computing the Renyi entropies? Are you just assuming the thermal density matrix?
Exactly, yes. I'm just assuming
but you might have thought that that's not the right thing to do for black holes.
Meaning, it's a classical approximation for black holes. That's all I'm doing. I'm doing classical processes.
Okay.
Yeah. It's not complete, definitely, but I mean, in the same way as looking at the area theorem for black hole evaporation is not good, right? I mean, once you take into account semiclassical corrections, all these.
I thought the right thing to do is actually do replica in this context, not just pretend that this is a thermal state.
What do you mean? I mean, so there are 2 equivalent ways, right, in which you can compute the Renyi entropies. I mean, we can start from the, I will show you the computation in the next slide, so yeah. And you can think about it in terms of replicas, definitely, I mean, but that will be the next slide. So what we can do instead with these constraints is to look at them for black holes in anti-de Sitter space. They can be thermodynamically stable, they can have positive heat capacity and be in thermal equilibrium with their own radiation. So actually they are canonical objects by definition. They have a temperature which is an increasing function of their size, and the infinite temperature black hole is thermodynamically stable in ADS. So what we will do for the main part of the talk is to look at these laws for black holes in anti-de Sitter and see what do they imply. And I stress that I won't make any use of holography, just indeed of the ensemble description of black holes. Okay, so the simplest example that we can look at, which is the,
sorry, could you clarify what the CPTP map you're looking at is? Is it time evolution plus coarse graining?
Exactly, yeah, it's some partial tracing because, I mean, we are looking at the merger, right? But the initial state is like the combined state of these 2 black holes, and the final state is going to be only the black hole. So we are ignoring all radiation that's been emitted. So in the same way, yeah.
Can you go into more detail about what that coarse graining is? Because I would have expected that the final ensemble that you have for the black hole is going to depend on the details of how you do that coarse graining.
That's true. I wish I could be more precise. I mean, I'm just taking in the same spirit as Hawking original computation. I mean, just looking at the initial states, just, I mean, 2 black holes, and final state, again, another, in the canonical, another thermal ensemble of a single black hole. I mean, in the same way as the first example that I gave you of applications of the area theorem by Hawking. So, yeah, I wish I could be more precise about the type of coarse graining, but essentially, I mean, it's again looking at this object and just from mean averages, deducing its thermal ensemble. That's what you do with, yeah.
But it's assumed that if I have 2 black holes in canonical, prepared somehow in a canonical ensemble respectively, after the time evolution, it will still be in a canonical ensemble?
That's what we are assuming. So here what we can do with these constraints is to rule out possibilities. So we can say, assume that we start with 2 black holes in the canonical and that we want to rule out final states in the canonical ensemble, and then we can rule out. Or we can say, assume we start with some other ensemble, microcanonical, and what can we rule out, for instance, in a canonical ensemble final state. So I will only talk about constraints between the same class of ensembles, but yeah, in principle you can ask, yeah.
Thanks.
So we don't know what's actually happening. I mean, that depends on all the specific boundary conditions and boundary terms and the details that you put. So we can just go in a negative direction, let's say excluding processes. Okay, so the easiest generalization, I mean, the direct extension of what we saw is just to look at the ADS4, Schwarzschild ADS4 black hole. So there, large black holes are thermodynamically stable above the Hawking-Page transition. So here L is the ADS radius. And we will also consider the simplest example, so the head-on collision of two black holes of identical mass, small m, which merge into a final black hole of mass capital M and work throughout in the canonical ensemble. So to evaluate the Rényi entropy in the canonical ensemble, so going back to the question before, so what we do is essentially, I mean, well, you can do it directly for the full system, just if you know how to write the free energy explicitly as a function of the temperature, and you can think about it also in terms of replicas. I will have a slide a bit later. But so essentially, I mean, well, this n beta, you can think about it as an auxiliary black hole or directly in terms of replicas. And so, well, okay, just by this simple algebra, in 4D we can evaluate it explicitly, and this is the form of the Rényi entropy. And so here is as a function of this reduced inverse temperature B that we defined. And now the Hawking-Page is at B equal to 1/2, so we are below 1/2. And in the n-to-1 limit, this is the ordinary entropy. And so one important point here, if we want to think about this construction in terms of replicas or auxiliary black holes with this temperature, is that we are evaluating the free energy by looking at the large black hole saddle, which is only dominant above the Hawking-Page transition. So to evaluate it, and we are not using the thermal ADS saddle, which is the dominant saddle in the other regime. So for that, for each, well, we want to restrict the values of n in such a way that we are always above the Hawking-Page transition, and we can always use this expression to evaluate the entropy. And so this sets a maximum value of n that we can achieve. If we want to go beyond this value, we should take into account thermal ADS. But I will stick to this regime. Okay, so given that expression, then we can try to use it to put bounds on the mass of the final state. So to do that in practice, we will assume that the two black holes have formed independently, so from two independent collapse, so that the initial state is approximately factorized. In this way, we can write the Rényi laws in this form, just as a function here as the black hole masses, and work out the constraints, which are very simple. But to be clearer, actually, I just plotted the results. So this is what you obtain for the lower bound on the mass of the final state. Oh, I have to speed up a bit. And for the mass of the final state as a function of the Rényi index n for a different initial condition. And here the dots are actually the points where these curves stop, and then the thermal saddle should be taken into account. Thermal ADS saddle should be taken into account. So this is n equal 1, and then we see that these bounds, they are stronger for n less than 1, and in particular the strongest bounds comes from the Hartley entropy.
Your initial state is two black holes. They're interacting. Why are they non-interacting state? And why does the replica just say it's twice the Renyi entropy?
Right, so that's what I said. So the way in which in practice we can compute this thing, otherwise we will need to evaluate the Renyi mutual information of these objects, is to assume that they formed independently for two independent collapses, so that their initial density matrix is approximately factorized.
I mean, look, the physical process is a dynamical one. We have two black holes, they evolve. I don't think you can do this calculation. It doesn't make sense to me that you can treat them as independent objects.
No, I mean, we're not trying to describe the interaction process, the merger process. We are just looking at an instant photo of the system once they are far apart enough. They form independently, they're far apart, they're very little correlated. And then we are looking, okay, this initial state, whatever the dynamics that happens in between, in what final state cannot end. And so we are able to exclude final states.
But they're not in independent universes, they're gravitationally interacting. So if I thought about this process in the dual field theory, well, it's a single initial state.
Exactly, but I mean, I agree that the full thing should take into account also this wiggle, let's say, and try to quantify the Renyi mutual information. We are just assuming that this is very little, and so that we can neglect it. I mean, in the same way as Hawking, when they did the original computation, did not look at the mutual interaction of these objects in flat space. He took them to be infinitely far apart and neglected any interaction whatsoever. Okay. Okay. So here, what I've plotted is the ratio of the two lower bounds that we obtained. So the one from n equal 1 and the one from n going to 0. So, and this is plotted as a function of the event horizon of the colliding black holes. So for large black holes that collide, these two bounds coincide, and this is because the large radii corresponds to large temperature in ADS, and at high temperature one can show actually that the Renyi entropies all become proportional to the entropy, so the constraints coincide. And then the largest correction instead comes from black holes, which are closer to the Hawking page transition. So this can be rephrased also equivalently as a bound on the amount of gravitational radiation that can be emitted, or the efficiency with which we convert the initial total energy into gravitational radiation. And this is a plot of the upper bounds on the efficiency, well, the one coming from n equal 1, the one coming from n equal 0, for some fixed temperature as a function of the radial distance, or here for a fixed radial distance as a function of the temperature. And again, the biggest correction comes from black holes which are close to the Hawking page. And I mean, this lower part of the graph should be neglected, because I mean, the two black holes actually have to be far apart enough so that they can collide, and that this whole approximation holds.
Sorry, question?
Yes.
In your previous slide, did you...
okay.
Sorry. Do you assume everything is happening essentially in a microcanonical window in order to apply these Renyi inequalities? Because you need a channel that preserves the maximally mixed state for this to be true?
No, we are working in the canonical ensemble.
But then should you not
the large black holes
compute the relative Renyies compared to the thermal state?
Sorry?
Should you not be computing the relative Renyies, like comparing the initial state to the thermal state, rather than using the Renyies themselves?
Why? I mean...
The derivation of the second law, you assume that the identity matrix was stable.
Exactly.
But here is supposed that the canonical one should be stable somehow.
Right, so the infinite temperature black hole here is stable in the canonical ensemble for ADS black holes. It's the large black hole.
Sure, it's stable, but this inequality was assumed, was based on the assumption that the maximally mixed state is preserved, which seems like a microcanonical statement, not a canonical statement.
No,
This
I
is
mean,
a-
it was just saying that the infinite temperature state is preserved, which is the case for ADS black holes here in the canonical ensemble.
But does that make sense for an infinite system?
Okay, so maybe let me continue. So what I will show you, it's another set of constraints which also give the same result, okay? So maybe that will be more convincing to you about the fine details. So what we are doing is indeed, it's I mean, I'm honest. So we are just taking the maximally mixed state to be, for this system, the infinite temperature black hole. So you're right, it's like infinite radius. This is stable, I mean, in this ensemble, and we are just going on from there, okay?
Okay, yeah, we can talk about it later.
Yes, we can talk later. Okay. So maybe I will speed up a bit. So then one can do it in general. So like other simple cases where one can get simple results to present are, for instance, supersymmetric extremal mergers. So this is because, I mean, in the zero temperature limit, the Renyi entropies all coincide with the entropy. And so then if we look, for instance, as the collision of two oppositely charged or rotating extremal black holes, and we rerun these bounds, we found now that so these are very simple to write, and then we find again that the optimal bound now doesn't come from the n to 0 extremum, but from the other extremum of the curves that we can reach, and this is essentially guaranteed by the monotonicity properties in n of Renyi entropies, that it's either one of the two. And okay, so this is just a plot of the upper bounds on the final reduced inverse temperature that we can obtain as a function of the entropy. Again, the second law and this optimal bound. And then grazie, thanks. And so then, in view of the recent understanding of near extremal mergers, one can look at also at near extremal black holes and their one-loop corrections to the entropy, to a partition function and thus to the entropy. One can look at the correction for Renyi entropies. So the effect of this correction is essentially to lift that zero temperature degeneracy of the Renyi entropies by a factor which is n-dependent but temperature independent. And then if one relooks at the bounds, the effect of this correction is essentially to relax a bit the constraints as compared to the supersymmetric case. So the dot dashed here was the upper bound from the supersymmetric case, and the solid lines, which you cannot almost distinguish, are the ones with near extremal corrections taken into account. Yeah, another case that one can study easily is the following. So again, if we consider oppositely charged or rotating extremal supersymmetric black holes, which collide and form a hot final state. So as t goes to infinity, the Renyi entropies factorize again in this form, and just rerunning the bounds, one sees that the strongest bound comes from the highest value of Renyi index n that one can reach. And extrapolating this just for give an estimate to the n to infinite limit, so to the mean entropy. This is the ratio of the lower bounds that one obtains for the final mass m. And this evaluates to 4 in 3D, 5 and 6 in 4 and 5 dimensions, just to give you an idea. So we are looking at a number of extensions of this work. So we are looking more in detail with a student, Emiliano Rizza, at charged ADS4 black holes. And this is because there is in the canonical ensemble, there is a window of the parameters in which we can have first order phase transitions between small black holes in blue at low temperatures and large black holes in orange. And so this gives new features and a richer structure in the Renyi entropies in the constraints, because now they can have discontinuous first derivatives. And another extension that we are been looking at is the following. And so this is based on the replica ensemble construction of Xidong, which associate geometric meaning to the normalized replica density matrix, and also makes manifest the ensemble dependence of Renyi entropies. Okay, so the normalized replica density matrix, if we think in a replica construction of these quantities as an associated von Neumann entropy, well, at high enough temperatures, once we are in a black hole state, which was also dubbed refined entropy, and it's related to the Renyi entropy in this way. So let me illustrate what I want to say with one example. So let's take one Euclidean BTZ black hole of given temperature and mass. This has a geometric area of the event horizon with associated von Neumann entropy. And at the level of this system, this von Neumann entropy can either be an entropy in a microcanonical ensemble with fixed energy, or an entropy in the canonical ensemble with fixed mean value. But now, once we construct the replica geometry associated to the normalized replica density matrix, one way to describe it is in terms of a Zn symmetric replica manifold. But then the construction now is sensitive to the ensemble that we started with. So in particular, what Xidong showed in this paper is that if we are working in a microcanonical ensemble, the replica manifold will be the same Euclidean BTZ that we started from, as in such a way as to keep the energy of the system fixed for each value of n. If instead we start from a canonical ensemble, the construction now is as boundary conditioned with a thermal circle which has length n beta, and in order to fill it with a smooth solution, one needs to rescale the mass of the black hole in such a way. And so then this has the consequence that the von Neumann entropy in the replica ensemble that we associate to the area of the event horizon of these two black holes gives a refined entropy, and also does a Renyi entropies, which is sensitive to the ensemble. So this is, at least to our knowledge, the first construction that made manifest the ensemble dependence of Renyi entropies. It was done in holography, but I mean, it applies generally. And so in particular, the refined entropy differs. So now, if we look at this, at this black hole in the replica, this at high enough temperature, I mean, dominates, and that's as an associated entropy, which is given by the area of its event horizon. But now this entropy satisfies in the replica manifold a second law, just as it was the case for the original system, for the evolution along this replica manifold time, lambda. But then through this identification, the von Neumann entropy of the replica manifold is the refined entropy, if we write it in terms of the original system described by the density matrix rho. And so the monotonicity of the von Neumann entropy in the replica manifold implies the monotonicity of the refined entropy, as long as the relation between time in the original system and time in the replica is monotonic. So this is to say that just by looking at the replica manifold black hole and its second law, we can derive another set of constraints. This is again a one-parameter family of constraints, which is given by the monotonicity of refined entropy, and which to distinguish from the other laws, because in general they are different, so these quantities are only, Renyi entropy and refined entropy are only equal for n equal 1, as they should, and n equal 0, but in general differ. We call them Hawking-Renyi second laws because they rely essentially on Hawking argument in the replica manifold. So this is another set of constraints which doesn't rely on CPTP evolution nor on the maximally mixed state being fixed, but just relies on, well, the replica manifold properties and it's the fact that it's, again, a BTZ black hole, and thus we expect it to satisfy the area theorem or second law. So we can rerun the argument and compute, well, it's immediate to compute the refined entropy of the full system. So this is for Schwarzschild ADS4. Again, we are only using the black hole, large black hole saddle, so we should stop at this value of n. And now if we look at these constraints for the same process as before, and we superpose the results with the lower bounds on the final mass that we had before. So the dotted lines were the Renyi constraints that I was showing you before, and now the solid lines instead are these Hawking Renyi constraints, or refined entropy constraints. So in general, they will be, just by their expression, they will be more constraining for n equal less than 1, as we see here. But again, the optimal bound again coincides with the Renyi entropy bound that we found before with completely different arguments. And yeah. And so, so as I said, we cannot apply the Renyi second laws to flat space black holes, but we can apply this set of inequalities to flat space black holes, and this is what we have been doing, and I hope to be able to report on these results soon. So these are just some plots to give you an idea. I mean, it's just evaluating this refined entropy and then using it to put constraints, just following the lines of what Hawking did. We cannot say more than what, let's say, Hawking, I mean, we can say more in the sense that we can be more stringent, but we are under the same assumptions under which we apply the area theorem to black hole mergers. And yes, so with that, let me conclude. So what I try to argue today with our proposal of looking at these Renyi laws for black holes is that in general they can put tighter constraints on gravitational dynamics than the second law. Very importantly, they give ensemble-dependent physical predictions, and this is just because by definition Renyi quantities are fluctuations dependent. And so what we are trying to do, which is the idea that motivated this work, is to try to pin down processes that can actually be informative for numerical GR and astrophysical mergers. And this is like a number of open points that can be interesting to show. So one was already raised, this Renyi mutual information correction to the laws. This one was, we also mentioned already, these H divergences, so the extension of these two corners of monotones to this much larger class, which are, however, in general much harder to evaluate explicitly. And yeah, some other ideas which I'll just let there. So thank you very much for your attention.
Thank you very much. Perhaps we can have time for one or two short questions. Please. Please don't. Oh, thanks.
So I'm just curious, given the various questions about ensemble, raised by ensemble and equivalence and so forth, have you tried testing your predictions against numerical relativity things at this point?
Right, so far, for what we have been able, they are compatible. And the point, I mean, is that, So if you look at the second law constraint, I mean, it's true that it's a constraint, but actually it's just a sanity check for numerical GR. And this is because, I mean, the results of mergers actually are orders of magnitudes away from the second law constraint. I mean, like 1 to 4 order of magnitude. So there is a lot of space actually for, yeah.
I realize numerical people don't do this, but if you did a head-on collision of two extreme Reiser-Nordstrom black holes, it would presumably be a lot closer to the bound than for Schwarzschild.
Right. So we are looking at
things.
charged black holes. Also because it's the easiest setting to look at to start with, and Kerr black holes also. Yeah, but yeah, head-on collisions, which I know they are not the astrophysical ones, but okay, it's already one step in that direction. Yeah.
Any further question? If not, let's thank Alicia again, please.
Thank you very much.